we introduced the concept of torque when we were talking about the work done on an object as it rotates. So what we want to do with this video is come back and give ourselves a better definition of what torque is, and then figure out how we're going to calculate the torque generated by a force about a particular pivot. So for starters, let's say I've got a long thin rod that's sitting here. And the first thing I need to figure out is what's the pivot point that this rod can spin around. When we talk about torque, torque is always defined relative to a particular pivot point. And so in this case, let's put the pivot point at the center of the rod. Let's say I've got a force labeled force 1 that acts at the rod's center. Well, that force won't generate any torque about this particular pivot. If I move that same force and move it over here a little ways to the right, well, now it will generate a small torque about that pivot that is going to make this rod start to spin clockwise. If I move that force even farther out, so now it sits over here where I've labeled it as F3, again, it's going to make the rod spin clockwise, but it's going to generate a larger torque. What torque is it's a measure of how much a force acting on an object causes it to rotate about a particular pivot. So what does the torque depend on? Well, just from our initial example, force 1, force 2, force 3, they're all exactly the same force, same magnitude, same direction, but clearly where they act along the object is different, and each of those generates a different torque. And so one thing that matters is going to be, well, what's the distance your force acts from the pivot? Let's take force 4, and again, it's going to act the same distance away from the pivot as force 3. Both of them act on the end of the rod, the pivot's at the center, so the distance from the pivot for both force 3 and force 4 is half the length of the rod. But force 4 is going to generate a smaller torque than force 3 simply because it's a smaller force. So the second thing the torque is going to depend on is what's the magnitude of the force. Let's take another force. We'll label it force 5, and notice it acts at the end of the rod just like force 3. It has the same magnitude as force 3, but force 5 generates a smaller torque than force 3 does. That's because the next thing that matters is what's relative orientation of the force. What we're going to see in a minute is that force 3, because it is perpendicular to the rod, it generates the maximum amount of torque that force can, acting at that point. Force 5, because it doesn't point perpendicular to the rod, it points back and makes some angle less than 90 degrees with the rod, it's going to generate a torque that's smaller. If I take a sixth force and add it out here, again, same force, so force 6 is the same magnitude as forces 3 and 5. It's still acting at the end of the rod just like forces 3 and 5, but force 6 generates no torque about this particular pivot. So in the same way we said you can look at force 1, force 2, force 3, and those forces are identical, but 1 generates no torque, 2 generates a small torque, 3 generates a larger torque. The same thing's true for force 3, force 5, and force 6. They're the same magnitude of force. They all act the same distance away from the pivot, but force 3 generates the largest possible torque, force 5 generates a smaller torque, and force 6 generates zero torque because of their relative orientation. The last detail that torque is going to depend on is, well, if we think about forces 2, 3, and 5, those are all trying to make the rod spin clockwise. Force 4, on the other hand, is trying to make the rod spin counterclockwise. And so the last detail that the torque is going to depend on is the direction that the force is trying to make the object spin. So the first three things we're going to put together to calculate out the magnitude of the torque generated by a force about a particular pivot. 4 is going to tell us about its direction. Things that have both magnitude and direction are clearly vectors, so this tells us that torque is a vector. So how are we going to calculate it? Well, again, we said the three things that torque cares about is the distance from the pivot, the magnitude of the force, and the relative orientation of the force. and all three of those things are tied up in this equation. So for starters, let's talk about r. r is the position vector of the force. It's the vector that runs from the pivot to where the force acts on an object. So if we think about force 1, because force 1 acts at the pivot, its position vector is the 0 vector. Force 2, it acts over here some short distance to the right of the pivot, and so its position vector runs from the pivot to where force 2 acts. Force 3 acts over here at the right end of the rod, so its position vector again runs from the pivot all the way out to the end. Forces 4, 5, and 6, because they act at the left end of the rod, all of them have the same position vector. So it runs from the pivot out to the left-hand end of the rod for forces 4, 5, and 6. So that's r. Well, what's phi? Phi is the angle between the position vector and the force vector. So what we're going to do to determine phi is we're going to draw in the position vector on our object, and then we're going to redraw the position vector and the force vector from the same origin, which makes it easy to see what the angle phi is. So if I draw in R2 and F2, because I'm trying to calculate the torque generated by force 2 about this particular pivot point, then when I draw them both in, I see that the angle they make is 90 degrees. So this angle that I've labeled phi 2 here is a 90-degree angle. So when I go to plug all this in, this is just the length of R2, whatever that distance happens to be. This is the magnitude of that second force, again, however hard that force pushes against the rod. And then this is a 90-degree angle. The sine of 90 degrees is just the number 1. So the magnitude of the torque generated by force 2 is going to be given by the length of that position vector times the magnitude of the force. Let's look at force 5. So again, I'm going to start by drawing in that position vector, and then I'm going to redraw the position vector and the force vector so I can see what phi is. And in this case, what I know is phi happens to be the same as the angle theta that I'm told, which is the angle that force 5 makes with the rod. So I can come back and calculate out the magnitude of torque 5, which is another way of saying the magnitude of the torque generated by force 5 about the pivot, and that's going to be equal to the length of that position vector, which runs from the center of the rod to the end, so that's half the length of the rod, times force 5, whatever its magnitude is, times the sine of the angle between those two vectors, which in this case we've said is given to us as theta. So if I think about this equation, what are the important details that I want to take away from what this equation is trying to tell me? The first one is the torque exerted by a particular force about a pivot is 0 if two things are true about that force. One is if the force acts at the pivot. So that's what's going on here with force 1. It acts at the pivot, therefore it generates 0 torque about that pivot. Or if the force lies along the same line as r. That's what's going on with force 6. So notice that both the force and the position vector for force 6 are perfectly horizontal. They lie along the same line. In this case, they point in opposite direction, which means that the angle between them is 180 degrees. But it doesn't matter if they point in opposite directions or the same direction, so that the angle between them would be 0. The sine of either of those values, 0 or 180, is 0. So there are two ways that you can have 0 torque generated by a force. One of them is to let the force act at the pivot, so r is 0. The other is to make sure that the relative orientation is either 0 or 180 degrees because the force and the position vector lie along the same line. Second important detail is I make my torque as big as possible, so I get the maximum value for the torque exerted by a particular force when the force is perpendicular to the position vector. That means that phi is 90 degrees, sine of 90 degrees is 1. The sine of any angle less than 90 degrees is something smaller than 1. So again, I maximize this equation when phi is 90 degrees. And again, if we think about force 3, it acts perpendicular to the rod Therefore, it generates the maximum amount of torque. Force 5, on the other hand, same magnitude force, same length of the position vector, but again, because it has some angle phi that's less than 90 degrees, you don't get as much torque as possible from force 5. That's because the more the force points along the line of the position vector, the smaller the torque is. If force 5 had been perpendicular to the rod, then it would generate as much torque as possible. But the more I swing it so that it lines up with a position vector, the less torque it generates. Of course, I don't have to rotate force 5 this way to lessen its torque. I can also rotate it the other way, and in fact, that's what's happened with force 6. So force 6, you took that force and you rotated it all the way around until, again, now it lines up with the position vector. This is our equation for calculating the torque done by a particular force about a particular pivot. There are a couple ways that we can interpret it. So interpretation number 1 basically says, well, let's keep that force and sine phi term together. I can think of them as the component of the force that's perpendicular to my position vector. And in that case, I can calculate the torque as just the length of r times that perpendicular component of the force. So if we come back to our picture, if you think about the torque generated by force 3, again, part of why it is a maximum amount is because all of force 3 is perpendicular. Force 3 only has a perpendicular component relative to that position vector. Force 5, on the other hand, it has a perpendicular component that will generate a torque, but it also has a parallel component of the force that won't. And so in rotating force 5 around, what I've basically done is made the perpendicular component of the force smaller and the parallel component of the force larger. The larger you make that parallel component, the smaller the torque generated by that force is going to be, which is of course what happens with force 6. Force 6 I've rotated all the way around, so it is only a parallel component. So force 6 generates zero torque about this pivot because there is no perpendicular component of that force. So only the component of the force that's perpendicular to r is going to exert a torque about a pivot. Well, the second way that I can interpret this equation is basically if I flip this around, and so now I've got the r next to the sine phi, and when I put those two together, that defines what's known as the moment arm or lever arm for a torque. So the moment arm is defined to be the perpendicular distance between the line of action and the pivot. And so I can then calculate the magnitude of the torque using this interpretation as it's the full force times this moment arm. And so that begs the question, well, if I want to think about the moment arm, what is the line of action? And the line of action, again, action was just the Newtonian way of saying force. So the line of action is just the way of saying what's the line that your force lies along. So the moment arm is the perpendicular distance from the pivot to the line of action. Well, force 1, the line of action runs through the pivot, therefore the moment arm is 0. Why force 1 generates 0 torque? It has no moment arm. Force 2, on the other hand, its line of action is some short perpendicular distance away from the pivot. Force 2 generates a small torque because it has a relatively small moment arm. With force 3, its line of action is all the way over here at the end of the rod, so its moment arm is half the length of the rod. The same is true for force 4. Its moment arm is half the length of the rod. Force 5, even though it acts at that same point, because its line of action does not run perpendicular to the rod, its moment arm is much smaller. With force 5, by swinging that force around, what I've done is I've shortened the moment arm. By making that moment arm shorter, I generate less torque by that force. Force 6, its line of action runs back through the pivot again, which means its moment arm is 0, which again is why force 6 generates no torque about this particular pivot. So I can reframe those key takeaway points and think about them in terms of the moment arm. And so the first one would be that if the line of action for a force runs through the pivot, and we said that was true for force 1, it was true for force 6, then the torque exerted by that force about that pivot is 0. 2, you get the maximum torque exerted about your pivot when the moment arm is as long as possible. And so again, how do you make that moment arm as long as possible? You want your line of action to be perpendicular to your object. 3, the smaller you make the moment arm, the smaller the torque generated by the force. So again, as you rotate your force around, what you're doing is changing its moment arm, and the smaller you make that moment arm, the smaller the torque generated by that force.